Hello, my little learners. In today's video, we are going to dive into chapter number 4, Exploring Magnets, from your Class 6 Curiosity textbook. So tell me, have you ever played with a magnet? Have you seen how it pulls some objects but not others? Sounds interesting, right? Well, then, let's get ready to explore the magical world of magnets, what they attract, how they work, and all the fun facts that make them so special. So, sit back, stay curious, and let's begin. Reshma lives in a coastal town of Kerala and is very fond of writing short stories. Her grandmother loves listening to her stories, so Reshma was writing a new story to share with her grandmother on her 60th birthday. The story was based on a ship carrying spices from Kerala for trade in the olden days. Reshma was aware that in those days the sailors used stars to find directions at night. But in her story, a situation arose wherein the sailors got caught in a storm with an overcast sky and stars were not visible. Reshma could not take her story forward as she could not think of a way for sailors to find directions. So she searched for information on the internet and her school library. She learned that the travelers used a device known as a magnetic compass for finding directions. Reshma had seen pencil boxes and purses which had magnets to keep them closed. A writing board in her school also had a duster with a magnet, but she had never looked at those carefully. She now became curious to learn more about magnets and magnetic compasses. So, students, Reshma lived in a coastal town in Kerala and loved writing stories. For her grandmother's 60th birthday, she wrote a story about a spice ship from olden days, but she got stuck. How would sailors find direction during a stormy night when stars weren't visible? So she searched and found that in olden times, sailors used a magnetic compass to find directions when stars couldn't guide them. That made her curious. She remembered how magnets are used in pencil boxes, purses, and even school dusters. And now she wanted to learn more about magnets and compasses. I know, my little learners, that you are curious too. So let's explore the magnets together. The magnets used by sailors in the olden days were based on naturally occurring magnets known as lodestones, which were discovered in ancient times. Later on, people found out that magnets could also be made from pieces of iron. Nowadays, we have magnets made of different materials. The magnets that you find in your school laboratory and those used in pencil boxes, stickers, toys are all artificial magnets. The magnets can be of various shapes, some of which are shown in figure 4.2. So long ago, sailors used natural magnets called lodestones to find directions. But today we use artificial magnets. We use these artificial magnets in many things like in pencil boxes, toys, stickers, and even in the school lab. Magnets come in different shapes such as bar magnet, which is like a straight stick, U-shaped magnet also called horseshoe magnet, and ring magnet. It is round like a donut. Now students, you might be wondering, do magnets stick to all objects or only to some special materials? And the answer is yes. Magnets stick only to objects made of certain materials, mainly metals like iron, nickel, and cobalt. So remember students, magnets attract materials that are magnetic and only a few materials are magnetic, not all metals. So let's explore what is magnetic and non-magnetic materials. Let us explore in activity 4.1. Collect a few objects made of different materials and also a magnet. Predict which of the objects will stick to the magnet. Write your prediction in table 4.1. Now hold a magnet in your hand and bring it near the objects one by one. Observe which of the objects stick to the magnet. Record your observations in table 4.1. So in this table, you can see that some objects are attracted by a magnet while others are not. Objects like nails, screws, key, stapler and tongue are made of iron or steel and they stick to the magnet. On the other hand, things like a wooden block, plastic pen, glass tumbler, candle, copper wire, handkerchief do not stick because they are made of non-magnetic materials like wood, plastic, glass, cotton or copper. This shows us that magnets attract only certain materials, mainly iron, steel or other magnetic metals. Sharpener have a metal blade so only that part is attracted. Was your prediction correct for all objects? Which material stuck to the magnet? What conclusion can you draw? Through this activity, we found out that some of the objects were attracted to the magnet and stuck to it, while others were not. The materials which are attracted towards a magnet are called magnetic materials. The metal iron is a magnetic material. Nickel and cobalt are other metals that are also magnetic. Some of their combinations with other metals are also attracted towards magnets. The materials which are not attracted towards a magnet are called non-magnetic materials. Which materials listed in table 4.1 were found to be non-magnetic? So wood, plastic, glass, wax, cardboard, copper, cotton, rubber are non-magnetic materials. So students, I hope you have understood what magnetic and non-magnetic materials are. The materials which are attracted towards a magnet are called magnetic materials. For example, iron is a magnetic metal. Nickel and cobalt are also magnetic metals. The materials which are not attracted towards a magnet are called non-magnetic materials like wood, plastic and glass. Do all parts of a magnet attract magnetic materials equally? No, they don't. All parts of a magnet do not attract magnetic materials equally. The ends of a magnet, called the poles, are the strongest parts. That means the magnetic force is strongest at the poles, north and south poles. The middle part of the magnet has weaker attraction. So, magnetic materials are attracted more strongly to the poles of a magnet than to its middle part. Now, let's understand poles of a. Let us investigate in activity 4.2. Spread some iron fillings, that is very small pieces of iron, on a sheet of paper. Place a bar magnet over them. Tap the paper and observe carefully what happens to the iron fillings. Do you observe anything special about the way they stick to the magnet? Do the iron fillings stick all over the magnet uniformly, or do the iron fillings stick more at some places? We find that maximum iron fillings stick near the ends of the bar magnet, as shown in figure 4.4, while a very few iron fillings stick at the remaining part of the magnet. If we repeat this activity with magnets of other shapes, do we get the same result? So yes, this is true for all shapes of magnets. Even if a magnet is in a different shape like a bar, U-shaped or ring, it still has two poles, a north pole and a south pole. These poles are always the strongest parts of the magnet, no matter its shape. You can see in these pictures that the poles attract magnetic materials more strongly and the middle part is usually weaker. So this is true for all shapes of magnets. These ends of the magnet are called the two poles of the magnet, the north pole and the south pole. Most of the iron fillings stick to the poles of a magnet of any shape. You might be thinking, what if we break a magnet from the middle? Will we get a magnet with just one pole? The answer is no. It is not possible to get a magnet with only one pole. If you break a magnet into two pieces, You will not get one piece with only the North Pole or one piece with only the South Pole. Instead, each piece becomes a new magnet with both North and South poles. Even the smallest piece of the magnet will still have both poles. So remember, a magnet with a single pole cannot exist. Poles always comes in pairs. Students, Reshma found out that sailors used a magnetic compass to find directions. But how exactly do magnets help in finding directions? Let's understand this interesting concept together. Let us experiment in activity 4.3. Suspend a bar magnet with a thread tied to the middle of the magnet as shown in figure 4.5. You may need to adjust the position of the string till the magnet is balanced horizontally. Now rotate the magnet gently in the horizontal direction and let it come to rest. Mark the position corresponding to the ends of the magnet on the ground or on a piece of paper stuck to the ground. Join these 2 points on the ground with a line. This line indicates the direction along which the magnet comes to rest. Now again rotate the magnet by giving a gentle push at its one end and wait till it comes to rest. Does the magnet rest along the same line? What direction does this line indicate along which the magnet rests? How can we find it? If we have noticed the direction where the sun rises or sets, we have an approximate idea of where east or west is. Hence, we can locate the direction along which the magnet. A freely suspended magnet comes to rest along the north-south direction. The end of the magnet that points towards north direction is called the north-seeking pole or the north pole of the magnet. The other end that points towards the south direction is called the south-seeking pole or the south pole of the magnet. A freely suspended magnet rests along the north-south direction because our earth itself behaves like a giant magnet. Repeat this activity with a small iron bar in place of the bar magnet. What do you observe? Does it always rest along north-south direction? It does not. It can rest along any direction. This implies that only magnets rest along north-south directions. This activity provides us with a way to test whether a piece of metal is a magnet or not. So remember, the north pole of a freely suspended magnet always points north direction, and the property of a freely suspended magnet to always rest along the north-south direction is used to find directions. Based on this, a small device called a magnetic compass was developed in olden days for finding directions. It has a magnet in the shape of a needle which can rotate freely. The needle of a magnetic compass indicates the north-south direction. The compass is kept at the place where we wish to know the directions. After some time, the needle comes to rest in the north-south direction. The compass box is then gently rotated until the north and south marked on the dial are aligned with the needle. Now all directions at that place are as indicated. So students, a magnet when freely suspended always points in the north-south direction. Using this property, people invented magnetic compass. This compass has a needle-shaped magnet inside it that can rotate freely. So when you place the compass at any location, the needle slowly comes to rest, pointing exactly north and south direction. Then we gently turn the compass box so the word N and S written on it match the direction of the needle. Now we can easily tell all four directions north, south, east and west with the help of the compass. Isn't that a smart way to never get lost? A magnetic compass is usually a small circular box with a transparent cover on it. The magnet in the shape of a needle is mounted on a pin standing on the bottom of the box. This needle is balanced on the pin in such a manner that it can move around this point easily. That is, it can rotate freely. The end of the needle which rests in the north direction is usually painted red. Below the needle, there is a dial with directions marked on it. How can we make our own magnetic compass? Let us construct in activity 4.4. Collect a few materials like a cork piece, iron sewing needle, a permanent bar magnet, a glass bowl, and water. Place the iron sewing needle on a wooden table. Then keep any one pole of the magnet at one end of the needle. Move the magnet over the needle along its length as shown in figure 4.7a. When it reaches the other end of the needle, lift it up. Bring the same pole of the magnet you started with to the same end of the sewing needle from which you began and repeat the previous step. Repeat this process at least 30 to 40 times. Now bring some iron fillings or steel pins near the needle. If the pins or iron fillings get attracted to the needle, then that means that the needle has become a magnet. Pass this needle through the cork horizontally. Float the cork in a glass bowl filled with water, such that the needle always remains above the level of the water as shown in figure 4.7b. When the needle comes to rest, your magnetic compass is ready for use. Note the direction in which either side of the needle points. Rotate the cork gently and wait till it stops rotating. Repeat this a few more times. Do the ends of the needle always point in the same direction? Much before the widespread use of the modern magnetic compass, a device similar to the compass needle made by you was used by Indians for navigation at sea. It consisted of a magnetized fish shaped iron piece kept in a vessel of oil. It was called Matsya Yantra or Mach Yantra. What happens when we bring two magnets closer to each other? So it depends on which poles of the magnets are facing each other. Like poles repel and unlike poles attract. So if you bring north to north or south to south, they push each other away. This is called repulsion. And if you bring north to south pole or south to north pole, they pull towards each other. This is called attraction. So like poles repel and unlike poles attract. Let's understand attraction and repulsion between magnets. Let us experiment in activity 4.5. Take a pair of bar magnets on which north and south poles have been marked. Mark the two bar magnets as A and B. Place the longer side of magnet A over 5 to 6 round shaped pencils as shown in figure 4.8a. Now bring one end of magnet B near the end of magnet A placed on the pencils. Make sure that the two magnets do not touch each other. Observe what happens. Next, bring the other end of magnet B near the same end of magnet A. Does the magnet A on the pencils begin to move? Does it always move in the direction of the approaching magnet? What do these observations suggest? So you will see that unlike poles of two magnets, that is the north pole of one magnet and the south pole of another magnet attract each other. The like poles, that is either the north poles or the south poles of both magnets, repel each other. Repeat the activity by using an iron bar in place of one of the magnets. What do you observe this time? You will find that both the ends of the iron bar will be attracted by both the north and south poles of the magnet. From this activity, we find that a magnet can be identified by its property of repulsion. Let us experiment in activity 4.6. Make a magnetic compass and a bar magnet. Place the magnetic compass over a horizontal surface and wait for its needle to come to rest. Now slowly bring north pole of the bar magnet close to the north pole of the compass needle as shown in figure 4.9a. Observe the compass needle carefully. What do you observe? Does the needle deflect? If yes, in which direction? Now repeat the above step with the south pole. Do you observe any difference this time? The compass needle is also a magnet. Will it show the same behavior if a magnet is brought closer to it? So, when the north pole of a magnet is brought closer to the north pole of the compass needle, it moves away as shown in figure 4.9a. When the south pole of the magnet is brought closer to the north pole of the compass needle, it moves 9 point as shown in figure 4. Suppose we place a piece of wood between the compass needle and the magnet. Will this affect the deflection of the compass needle? Let us investigate in activity 4.7. So repeat the first or second part of activity 4.6. Then, without disturbing the bar magnet and magnetic compass, place a piece of wood between them, perpendicular to the table as shown in figure 4.10, and observe the compass needle carefully. Is there any effect on the deflection of compass needle due to the piece of wood? Record your observation in table 4.2. Repeat the process by replacing the piece of wood with a cardboard sheet, thin plastic sheet, and a thin glass sheet. You would observe that there is no appreciable change in the deflection of the needle when a sheet of any of the above material is placed between the magnet and the compass needle. Therefore, we can conclude that the magnetic effect can act through non-magnetic materials. Let's do some fun with magnets. So, after learning about magnets, Reshma was excited and decided to set up some fun activities using magnets at her school fair. You may try making these yourself and may also think of some more. We can make a garland because magnets can move some objects without touching them. Isn't that amazing? We can also take the steel balls out of the maze by moving a magnet below the or we can pick out a steel paper clip fallen in water using a magnet without getting our fingers or the we can make two toy cars move towards each other or away from each other by using the attraction and repulsion properties of magnet poles. Because if we place opposite poles, that is north south, facing each other under the cars, they'll attract and move closer. But if we place same poles, that is north north or south south, they'll repel and push each other away. Students, do you know in some magnets the north and south poles are marked as N and S? In some other magnets, the north pole is indicated by a white dot. Sometimes the north pole of a magnet is painted red and south pole is painted blue. How to keep the magnets safe? So, magnet says, store me properly. Keep me in pairs with unlike poles on the same side. Keep a piece of wood in between. Place two pieces of soft iron across the ends. Do not heat me or drop me or hammer me. Do not keep me near mobile phones or remote. In the next That's all for today, students. I hope you enjoyed learning about magnets and now understand them really well. In the next video, we'll go through the question and answers from this chapter. Until then, keep exploring and stay curious.